Hello, here we are once again. It's the physics video lecture. Physics 4B video lecture 4. So I had a lot of people asking about some of the homework problems. So I think I'm going to begin with some homework problem review, and then we'll continue on with our new materials. So the homework problems that people were interested in having discussed were Chapter 20, Problem 26. Now that was the period of a pendulum. I'm going to use lowercase t because uppercase T is being used for temperature most of the time. So yeah, we have this 2 pi root L divided by G. That's the period of the pendulum. And we see that if the pendulum increases in length, for example, by thermal expansion, then that the period also increases. And so the clock's actually going to run slow. Okay? It's going to take longer to go tick-tock. Now, this is a nice application of some calculus. So suppose we just take a derivative, dt dl. We'll take the 2 pi over root g out of here, and then we've got the derivative of the square root of L, which is 1/2 square root of L down here. Okay. Now let's go ahead and arrange this. So dt is equal to 2 pi again. Well, we'll do this in a couple steps. 2 pi over root g, 1/2 root L. Now let's go ahead and put the dl in, okay? But the dl, I'm going to cross multiply over here, is going to be alpha L d temperature, because that's the temperature law, right? Delta L is equal to alpha L0 delta T. So since we're doing this as a derivative, we can write this as delta time is equal to 2 pi. Now we're going to take the square root, L over the square root of L is the square root of L, is the square root of L. So we will have 2 pi square root of L over G again. And now we're just left with 1/2 alpha delta T. So 1/2 alpha delta T, that's alpha, and that's the change in temperature. So this is pretty interesting, and this here is the original time. So we have the change in the period divided by the original period. I'm just going to divide that over there, is equal to 1/2 alpha delta temperature. And it's from these numbers here, for whatever the brass rod was in delta temperature, that'll get you that relative change in time. And that happens for every time it swings back and forth. So if you have a full day's worth, then you can figure out the fraction of an entire day. Okay, the fraction of an entire day. If this is a day, then that's the fraction of the entire day. And this was just so and so many degrees Celsius. Okay, so that's actually a trick to remind yourself of. That's kind of an important property of the derivative and how we interpret the derivative. You know what I'm doing is this. Y equals f of x, and then I have these approximations. Delta y is equal to f prime of x delta x, and since it's not strictly an equality, good, and equality, it's an approximation. Okay, so that one is definitely worth talking about. Next problem, thermal expansion. And what else did we have here? Yeah, problem chapter 20, 27. This is really basic. So you have your law for linear expansion, delta L, alpha L naught, delta temperature. And in this case, we were asking for a delta temperature. So we're simply solving for delta temperature, delta L, alpha L naught, and then we're plugging in the numbers we were given. This was a diameter, and this was a change, you know, the other diameter, so you change in diameter. So that one shouldn't give us any problem. And I have here also a question about chapter 17, problem, was that what, 70? 70. So now you've got the V root mean square. You're looking for this 3 K Boltzmann temperature over M. And what you were going to do is plug in the mass of 2 protons. That's the mass of the hydrogen molecule. Okay, you plug that in there and plug in all the numbers. That's for number 70. What else do we have here? Then we had 66, 67, and 68. So for 66, you have that distribution of speeds for, let's go ahead and write it out. F of V function, distribution function of the speeds. We have we have 4 over root pi. We have M over 2 K Boltzmann temperature to the 3/2 power. And then we have what's important, V squared e to the minus mv squared 2K Boltzmann temperature. So it's really this thing that you have to differentiate with respect to V. Okay, those factors in front don't matter. You have to differentiate this object right here with respect to V and set the derivative equal to 0. And then you'll find, you know, you've got a product rule here. You're going to have 2 expressions, set them equal to 0, and then you're going to find that V most probable, oh yeah, so this distribution, you know, it looks like this. It's a probability distribution. So the most probable is really where this thing has its peak. That's why you could use the first derivative criterion. And then, so they gave it to you, it was going to be root 2 K Boltzmann T over M, most probable root. So you'll find that without any problem either. Okay, someone had a question about 17, chapter 17, problem 67. And the problem was with the formula they gave you in the book. So sometimes you're going to have to look these things up in an integral table. The formula they give you for that integral is wrong. I will just go ahead and, it's off by a factor of 2, or it has a square root sign where it shouldn't. So the correct formula will give you the answer you're supposed to get. And yeah, so 17, problem 67, integral 0 to infinity b squared e to the minus a b squared, where a is a constant, dv is equal to root pi divided by 4, not root pi over 4. That puts you off a factor. A to the minus 3/2. So it was that mistake. There was a mistake in the book. This is the correct formula. Give you the right answer. 1768, you're going to integrate, you know, since this is your f of v without that 4 factor. For 1768, you were just going to integrate v cubed e to the minus ab squared dV from 0 to infinity. And there, the formula they gave you in the book was the correct one. So there you have it. So that's the homework problems. If you have questions on these homework problems, just write to me, email, maybe when you're turning the assignment in, but actually anytime, and I'll try to get back to you on that. So that's where we are with regards to that homework assignment number 1. Okay. So the next thing we're doing is talking about heat capacity, continuing on with heat capacity on into calorimetry. You may notice, I'm sure you can't not notice, that I'm bouncing around in those chapters. And the reason for that is that we really need material in chapter 20 to do a systematic discussion. For example, we needed thermal expansion to properly talk about thermometers and things like that. That was in chapter 20, and yet I started off with that. So I'm going to continue doing that, and I'll even lay out the logic of what I'm doing every now and then. It's the more logical way, what we're doing here. What we're basically doing is we're taking the essential phenomenology of the subject first, the things that really don't require the molecular view. The exception to that is the molecular ideal gas. That we did because we wanted to make contact with energy concepts, work and kinetic energy, and so we had to go into the molecular theory because we wanted to put thermal physics on a physics basis, and we needed the energy in those concepts. But other than that, I'm following the phenomenology, and so we will be bouncing around in these chapters, but it is the more logical progression. Okay, so having said that, let's go back to what's on our plate here. Yeah, heat capacity. So we're in thermal physics here, so I'll write that down. And what we left off with was, after we had the mechanical equivalent of heat and that whole development, which again, we tied work and thermal energy together, so that's very important. We had the specific heat capacity. I'll just call it specific heat. And what we're looking at is Q mc delta T. And the idea is we introduce heat into some system here, of mass m, temperature T. We introduce heat there and the temperature increases. We can also have, and so delta T would be positive, T final minus T initial, by introducing that heat. Okay. And so M is mass, the specific heat capacity as the units joules, right? Because we had the mechanical equivalent of heat, and now we know that thermal energy can be measured in joules. Good. So joules per kilogram degrees Celsius. Okay. And I even had asked you guys to put together a table of some of these values. I gave you 3, you can get another half dozen or so. Have them in your notes, that way you're aware of them. Okay. So yeah, that's a specific heat. And if the delta T is negative, then that means that energy left. So energy can go in, energy can flow out. So thermal energy flows in, flows in, we'll just use that expression, flows in, and and temperature increases. Good. However, there's an exception to this when thermal energy can flow in and the temperature not increase at all, and that happens during a phase change. So briefly, phases of matter. Well, we have solid, liquid, gas, and actually plasma. Right now we're going to be concerned with solid, liquid, and gas. This is in the molecular and atomic scale where the charges are actually separated from each other. But if we do solid, liquid to gas, draw a nice little picture. So here's an ice cube, and you add energy to it, and it melts and turns into water. And you add some more thermal energy. Here I'll draw a balloon, right? And there would be your solid, your liquid, your gas. And as we add energy to the solid, turns into a liquid, we add thermal energy, turns into a gas, okay? And the interesting thing is, with these phase changes, you can go from a gas back to a liquid, go from a liquid back to a solid. And so you increase the thermal energy, or you release the thermal energy, okay? So the substance can absorb thermal energy, and down here it would release thermal energy, okay? So what we're going to do next is just look at this really stereotypical graph of these processes in terms of their energy. Introduce a couple of concepts. So what we're going to consider is starting with some ice, some chunk of ice, say a kilogram, and gradually adding energy to it, thermal energy. And we're going to record the change in temperature. So here's a big half-page graph. This one's good to do sufficiently large. Go like this. And we'll call it add heat to 1 kilogram of water. Although the amount of water there doesn't really matter. So here we're adding thermal energy in joules, and here we're registering the temperature, say in degrees Celsius. So let's go ahead and start. I'll actually get a scale going here. So I'm going to call this 100 degrees Celsius, and this will be minus 20 degrees Celsius. So we've got a chunk of ice at minus 20. We add some energy very slowly. You know, turn the dial on the freezer from minus 20 to minus 10 to minus 5 to minus 1. And eventually, you know, its temperature will increase till it gets to 0. And the amount of heat involved here is Q is equal to mc sub ice delta T. That's the formula. So what happens when it reaches 0, you keep adding energy to it, the temperature stays the same, but the ice melts. So this curve has a horizontal section, this graph, that's melting. So that's interesting. It's melting, but the temperature is staying the same. You do it very carefully until it's all melted, and then you have this mass of ice that's been turned into water. So the energy associated with this, Q is equal to the mass times the latent heat of fusion. So you're going to have to look up latent heats. Latent heat of fusion it's actually quite a bit latent heat of fusion for water, I think it's 3.33 times 10 to the 5 joules per kilogram. It's quite a bit of energy. So it melts, it's all melted, and now the temperature increases to 100 degrees, and of course we know this law. This is the Q equals MC water delta T. All right, so if you had a kilogram, you'd have 4,186, 4.186 times 10 to the 3, 100 degrees, 10 to the 5. So 4 times 10 to the 5 joules, which is not that much more than 3 times 10 to the 5 joules for the latent heat of fusion. And bringing water from 0 to 100 degrees takes a lot of energy, so you realize the melting is actually taking an enormous amount of energy. Then we have, at these temperatures, at this temperature 100 degrees, we're just going to add energy and vaporize that water. So this is vaporization, and there the Q is the mass times the latent heat of vaporization. ML sub V, L sub V for water, so that's liquid to steam, liquid to gas, is 2.26 times 10 to the 6 joules per kilogram. Takes an enormous amount of energy to vaporize this kilogram of water completely. Okay, so these latent heats are quite interesting because we're adding all that energy. We're not changing the temperature, but we are changing the structure. We're going from a solid to a liquid, we're going from a liquid to a gas. And these are pretty enormous energy quanta, which is interesting also. You're used to adding thermal energy to melt and to vaporize, but we're not as accustomed to thinking that that much thermal energy will be released, returned to the environment, so to speak, when we go from gas to liquid and liquid to solid. So yeah, maybe I should have labeled this a little better. You guys can do it, fill in some words here, what was going on. And there's the graph. And as far as these latent heats of fusion, maybe you add a couple of these out of the book, 2 or 3 to your notes. Same with the vaporization. There's also the melting temperature. Here we're just talking about water, so it's 0 degrees Celsius. But for many different substances, you'll have a whole list of them. You'll get the melting temperature, you'll get the vaporization temperature, typically under atmospheric pressure, and you'll get the latent heat. So look up the tables of these things in your book. So tables of values for T melt, T vaporize, and also latent heat of fusion, latent heat of vaporization. So you get a table of those. You can put a couple of them in your notes if you want. Good. So now with this background, you can do some calorimetry problems. I'm definitely going to put basic calorimetry problems on some of our quizzes. So the next topic here is calorimetry. And we'll assign a couple of these out of the book. So calorimetry, it's really the application of these concepts here. So let's just do an example. Suppose I take ice, M sub ice at T equals 0 degrees Celsius. I'm going to dump it in a beaker of water. So M of water at, say, T equals 90 degrees Celsius, okay? The idea with calorimetry is we want to find the equilibrium temperature. After the ice all melts, the energy is going to come from the warmer water. It's going to melt the ice and bring the temperature of the ice up. And so what we imagine is that this thing is isolated. No energy coming in or going out of this system. And if we neglect the mass and specific heat of the beaker for now, just to keep it simple, we have Q total is equal to 0. What that means is the total energy exchange in this thing is equal to 0, because nothing came in and nothing went out, just these constituents. So here's what we would say. We would say mass of the ice, latent heat of fusion of the water, okay, plus the mass of the ice times the specific heat. So that's going to melt it. Okay, actually, let me write it this way. Q of melt the ice. Okay, that's one quantum of heat plus Q of heat the ice water plus Q of the water in here, so the rest of the water is equal to 0. Okay. So now this is going to be great. So here we're going to have M ice latent heat of fusion plus mass of the ice, but now it's melted, so it's specific heat of water, T final minus T 0 degrees Celsius. So we can actually just put a 0 here, but I'm just putting it as the delta temperature. This is 0. Plus mass of the water, T final minus temperature of the water equals 0. Sometimes people balance these equations out, one side equals the other. In my opinion, it's much better to do it this way because the signs are going to take care of themselves, okay? This is going to be positive. The final temperature is going to be less than the initial temperature. This is going to be negative. The sign's going to take care of itself. You have one equation you can solve for one unknown. If there's not enough energy in this water, the problem gets a little more difficult because then only part of this ice is going to melt and the final temperature will be 0. So you have to monkey around a bit with the numbers to see which is the case. Okay. But for example, if I have, a kilogram of ice and 2 kilograms of water at this high temperature, guaranteed to work. Okay. But yeah, so this is how you set your calorimetry problems up. And I like this 3-step. Total energy change is 0, or the total energy flow is 0, and then you have these constituents. Ice got melted, water that was ice got heated up, and all that energy came out of the water in the bucket. Okay, so that's a good one. It involves the latent heat, so that's good as well. If you're bringing some hot steam into the mix, you could have some condensation of the steam to water, and you would have a mass of steam, latent heat of vaporization. So there's a calorimetry problem. Let me write a couple more up here. Yeah. Let's do an even more basic one, where we'll do some numbers right now. These, of course, need calculators because of the values of these things, but there are some where we can keep it really simple. For example, so here's another calorimetry example. This time I'm just going to take 2 glasses of water. One warmer, one's cooler, they're both liquid, I'm just gonna pour them in, and after they come to equilibrium, what's the final temperature? Okay. So this example is M1 specific heat of water T minus T1. You know, better to follow my own advice up there so it's transparent. Basically, we're mixing these two glasses of water together. Okay. Again, this could have been water added to water. It's encased in that red box, nothing's coming in or leaving. So here we would have M1 specific heat of water T minus T1, which is the initial temperature, plus M2 specific heat of water T minus T2 equals 0. So this is a nice case because common specific heat drops away. We have some chance at solving this. So let's go ahead and we'll have M1 plus M2 times that final temperature is equal to M1 T1 plus M2 T2. So T final, M1 T1, M2 T2 over M1 plus M2. Well, you're going to get, that's like an average type of quantity of value. So that's very basic. For example, equal masses of water, you literally get the temperature between the two original ones. Okay. So take this and do some examples. If M1 equals M2, then the temperature is equal to T1 plus T2. Right, so pulled out the M1, and then 2M1, 2 in the denominator, literally the average of the two. Okay, so those are two good calorimetry examples, one of them with the latent heats and one without. And of course, with different masses, different specific heats, you're going to have to use a calculator to tease out the actual number. Okay, great. So I'll assign a couple calorimetry problems, and you guys can do a little bit with that. Good, so now I'm jumping into chapter 20 again. So after calorimetry, I want to talk about heat transfer. You notice we are talking about heat transfer, and we have to get a little specific about it. Here it's been just abstract. We had one temperature, we had another. We wait long enough, we get equilibrium. So our next topic is heat transfer mechanisms. This is in chapter 20. We really need to talk about this because the basic fundamental law that we're dealing with is that energy flows from a higher to a lower temperature object, okay, spontaneously. So I like to, I'll just write this, energy flows or is transferred, put that in scare quotes for you, energy is transferred. And here's the thing, suppose you have an object at a higher and an object at a lower temperature, so as in hot and cold, hotter and colder. Then if you bring these into contact with each other, so they're here in contact with each other, isolated from everything else for the moment, how's the energy going to flow? Okay, well, this is a fundamental law that's observed, and no one's going to argue with it. You bring them into contact with each other, energy flows from the hotter to the colder. We assume that up there. Okay, energy flows from the hotter to the colder, and if they're in contact long enough, they can reach an equilibrium where their temperatures equalize, and that was, of course, the idea with these two water, hot and cold, that we put together, and they equalize at the average. So the question is, by what means can the energy get from one object to another? So we're talking about heat transfer, and what we want to know is what are the mechanisms. Turns out there are only 3 that cover everything, so that's pretty fundamental. From TH to TC, hotter to colder. And this is going to be a violation of a fundamental law if, for example, this water gets colder and this water gets hotter. No, energy conservation would not be violated. The quanta of energy could be fine, but it's not going to happen that way. And if it does, this is so fundamental, if it does, and you're watching a movie of it, that movie is being played backwards. Okay. So, what are these mechanisms? There are 3, and I'm going to list them first, because you can start to memorize them: conduction, convection, and radiation. All very interesting, and I'll bring some demonstrations if I can get them set up the function. I have some good demonstrations of each of these, but we're going to start with the heat transfer by conduction. So conduction refers to actual physical contact of molecular collisions. Conduction, the demonstration that I'll just describe and that you guys can do in many different forms is if you have a metal bar and you apply a flame over here. I'll pretend it's our butter candle. Then if you wait long enough, this is going to get hot, and then the heat's going to travel along the length of it. Okay. That's heat transfer by conduction. And the reason we say it has to do with molecular collisions is because from molecular kinetic theory, we realize that the molecules are agitated, they're moving faster, they're kicking their less agitated neighbors into motion, and so eventually that agitated molecular motion is transferred all the way down to the end of the bar, and this end will be hot as well. So that's the idea of heat transfer by conduction, and we'll just write here molecular collisions. Now, there's a formula given for this. It turns out that if this bar is made of aluminum, and the second bar is made of steel, the aluminum will actually conduct the heat much better, much more rapidly. We used to have a demo where we put little wax plugs on the end of these bars and then see which one melts off first. And the aluminum gets hot much faster at this end, and the wax plug will drip off, okay? So you got that idea of molecular collisions. So there is a material constant specific to the different metals, and I'll give you the formula for the power that's transmitted thermally is delta Q over delta T. And let's see what letters we're using today. K, that's right. Power, we're using in our book the letter I. I'll go ahead and write this down. It's got a minus K A D temperature dx. So this is power. So this is power. I is, I could write delta Q, dq over dt. Joules per second, watts is power. Okay. But let's go ahead and look at this formula for a moment. This is the material constant, thermal conductivity. Go ahead and look in your book and write out 2 or 3 of these just to compare the range. You know, you would have glass, aluminum, steel, and they'll have different thermal conductivities. The larger this number, the more power is being transmitted there. This is the cross-sectional area. Cross-sectional area, and this is a gradient of temperature. So if we have, say, imagine we've got a slab here of this material, and here's our x-axis. So we have temperature on one side, temperature on the other side, cross-sectional area, delta x in thickness, okay? Then, if T2 is greater than T1, then delta T is positive, okay? But that would mean the energy would be flowing from right to left. So if T1 is greater than T2, the derivative is negative, and minus sign makes it positive. That's the reason for the minus sign, just to get the proper direction of flow, in keeping with that up there. So this should make complete sense. We could also say I is equal to K A delta T over delta X in terms of the thickness, and this is just the magnitude, right? We don't have to worry about the sign. And you can see, the greater the area, of course, the greater the energy flux. Twice as big area, twice as much energy can go through. You can also see the delta X in the denominator. If it's thicker, you're going to get less energy flow. If it's thinner, it's going to be more direct. So this is a really sensible and intuitively correct formula. Okay. Now there's a homework problem that I want to set up for you guys. Yeah, we got a couple minutes. So yeah, I'm going to give a couple calorimetry problems, and I'm just going to assign one of these because typically, you know, they just plug it in. Not such a big deal, but there's a really interesting one in the book. So we'll use that formula, and let me describe it first. The idea is that instead of a slab, you know, with that cross-sectional area, so let's call this homework problem and I'll assign it. What we have is a sphere. Okay, so there's a sphere with a hollow inside, and you've got the material here, and let's just call this A, and this outer radius B. And you know, there's a material constant K, so this is a sphere, hollow sphere. And so if you have one temperature on the inside and one temperature on the outside, given these values, K, A, and B, what is the heat flux power through this thing? It's no longer a slab, but rather it's this sphere. And so what you're going to do is just take some surface right between A and B, And you know, your area for the heat flux there. Now the heat flux is going to actually be the same everywhere, beginning to the outside. So you're going to have the area is going to be 4 pi r squared. Okay. That's an r right there. So you set this up, and they'll lead you through it. It's nice, and you'll do an integration. To solve the problem of the heat flux through this sphere. So you can imagine, you have temperature here, say it's higher on the inside than the outside, but the specific geometry is going to give you the amount of heat that comes out the outside. Okay. I think that's enough said. I think you'll enjoy that. Give it a try, and of course, you can email me if you need some help on it after you've given it a try. But yeah. So we could write that we've got temperature sub A here, temperature sub B there. That's our delta temperature. And what is the heat flux through there? See, if it were a very, very thin shell, you'd have area 4 pi r squared, and your thickness would be dr. Would be dr, but instead we have a finite difference a to b, t sub a, t sub b. Okay, I'm going to leave it at that. Let me not forget to write the homework assignment up on the board. Homework from the 4th lecture. Let's see what we have here. Hope I wrote it down. Yes, we have chapter 18. Chapter 20. Now the problem from chapter 20 is 39. That's the one I just described right here. Chapter 18. I have 29, 40, 42, and 48. Good. See you guys next time.